The inverse of a matrix is another matrix which by multiplying with the given matrix gives the identity matrix. There are many ways to find the inverse matrix: the montante method, the adjoint method, and the Gauss-Jordan elimination.
As you can see, this is a solution. The matrix A is of dimension n by n and contains in each row the coefficient of the unknowns of each equation. Matrix X is the dimension n by 1 and one column and contains the n unknowns of the system. And matrix B is the dimension n by 1 and contains the independent terms of the equation. As here's most explicit, as you can see in the equation in the presentation. Ax equals b as a at the minus 1 by ax equals a at the minus 1 by b as the x equals a at the minus 1 by b.
Suppose we have a system of n linear equations with n unknowns, and we can represent the system in matrix form as we explained the inverse method to solve certain comparable systems of linear equations with a solution. Calculate the solution by multiplying the matrix of the system. Although for this process to work, we need to accomplish some requirements, because for an inverse matrix to exist, the determinant of said matrix must be different of 0. If not, the system may have no solutions or infinite solutions. Also, the matrix must be in an n for n configuration, so the determinant can exist in the first place.
And so, for our example for this project, we have 4 functions that we have to pass to the matrix, and then in the layer B, on the upper layer we find the equations, and the lower layer we find the functions.
Okay, as we already know, we can get the inverse matrix by a lot of different methods. In this case, we're going to be using the Gauss-Jordan method. And it's pretty simple, really. It's just a little bit tiresome, but it is kind of simple. First, as you know, we have to take the original matrix and augment it, by adding the identity matrix on the right. Then we will proceed to be doing a lot of elemental operations to the complete rows, just in order to convert the original matrix on the left into the identity matrix, so that the matrix that we will have on the right is going to be, the inverse matrix. The several kinds of operations that you can do are multiplication, swapping, adding, and subtracting. But just you have to take into account that whatever you do to the left side, you have to do to the right side too. And as I said, when you get the identity matrix on the left, the matrix that you will have on the right is going to be the identity matrix. I'm going to explain a little bit more specifically for this example. You can see that the first row you have to multiply by half and add it to the second row. Then the first row you multiply by -3 and add it to the third row. After that, the first row you have to subtract it to the fourth row, yes. And the second row, then you multiply by 2/7, and after that by 7/2, and you have to add it to the third row. The second row you multiply by -1/2 and add it to the fourth row. Then the third row you multiply by 1/7, then by 5/7, and then you add it to the fourth row. At this point, you can see that we almost have the first half of the identity matrix on the left side. We have to keep going. Then you multiply the fourth row by 49/6, and multiply once again by 3/7 and add it to the third row. After that, you multiply the fourth row by minus the seventh, and then you add it to the second row. You multiply the fourth row once again by minus 3/7 and you add it to the second row. And multiply the third by a half and then add it to the first row. And just as the last step, we have to multiply the second row by a negative half and then add it to the first row. And now we have the inverse matrix.
Well, another way to find the inverse matrix is by using the adjoint method. This method basically consists in using this formula, that is multiply the inverse of the determinant times the adjoint matrix. And the adjoint matrix in this case is calculated by, first of all, we have to find the transpose matrix of the principal matrix, that is A in this case. And after we have the transpose matrix, we have to substitute each one of the terms in this matrix by the corresponding cofactors of each term. And after that, we will get this matrix that is here, and we could multiply this matrix times the inverse of the determinant, and the determinant we could calculate it by any method we want, like montante, cofactors, etc. And after doing this multiplication, we will get the same matrix, the same inverse matrix, in fact, like another method, that is the Gauss-Jordan methods.
Well, now that we obtained the inverse matrix by two different methods, we are sure that we can now obtain the X matrix that contains the values of the variables that we're looking for. How? Well, we use the equation that we learned at the start of this video, the one that says that the A matrix times the X matrix is equals to the V matrix. And after changing and separating some terms, we know that the X matrix containing the variables is equals to the inverse matrix of A times the matrix of the independent terms, or V. Now, so we have to now do the multiplications in the table to obtain set values. After that, we obtain a 4-row, 1-column matrix that has the 4 values of the variables that we want to know. The thing is, we can be sure that set values are correct. How can we be sure of set values? Well, we have to substitute set values in the original equations that we were given at the start of the problem. After substituting set values in the equations and knowing that the 4 of them are correct, we can be completely sure that the variables we obtained are correct. And with that, we end the video.